transfer. Today we're going to just continue on for about 30 minutes in the material on chapter 8. And then at 10 o'clock, I'll break so you can have 5 minutes or so to just prep yourself to get ready for the exam that opens up at 10:05. So I'm going to start sharing my screen again so we can pick up where we left off the last time. We considered that, let's see here. For internal flow through a pipe, we can have two conditions, a constant heat flux problem or a constant surface temperature problem. Going back to what we were considering the last time, when we have a constant heat flux applied to a pipe for the heating of a fluid from its inlet to its exit, the temperature variation of the fluid as it moves through the pipe is going to be linear. The expression of the temperature temperature variation of the surface of the pipe is going to vary in the entrance region, and that's just because the heat transfer coefficient is going from a high value to a lower constant value at the end of the entrance region where it becomes constant. And at the end of the entrance region, the variation of the temperature of the surface will be the same as the rate of variation of the temperature of the fluid. So there's a parallel line or a distance between the two lines such that they travel parallel once we're in the fully developed, that's actually thermally fully developed region. So that when we have a constant heat flux, the temperature on the surface will vary. So for a constant surface heat flux applied, the surface temperature will vary. For another problem where we consider a constant surface temperature, now this might be carried out if we're heating a fluid by having a saturated condition on the outside of the pipe so that condensation occurring on the pipe. That condensation would occur at a constant temperature and give us then a constant surface temperature. If that surface temperature is higher than the temperature of the fluid that's moving through the pipe, then it will heat up such that its maximum temperature at which it can leave the pipe would be that surface temperature. For a constant surface temperature problem, the heat flux is going to vary as a function of position. Now, for this problem, the expression of the temperature variation as a function of position for the fluid is one that has a different shape. Here, whatever the inlet temperature is, there will be this exponential decay of an increase in the temperature up until it gets to the surface temperature. Whereas for the constant heat flux problem, for as long as we apply a heat flux, the temperature of the fluid will vary linearly for that constant heat flux. So in order to write an expression for this line that is the mean temperature of the fluid, T sub m, and again, it's called a mean temperature just because the temperature variation at a particular position along the length of the pipe is going to take into account the temperature variation through the radius of that of the pipe, where we have if it's in this case, like a fluid that is heating up, the highest temperature of the fluid will be around the radius, and at the center line, it will be its lowest, but an average temperature at each position can be used to calculate what we call a mean temperature. Now, in order to get an expression for the mean temperature of the fluid as a function of x, in the previous problem, we developed an expression when we had a constant heat flux, and that was just the mean temperature of the fluid as a function of x. It's just a linear variation in that. It was the heat flux times pi d over m dot c sub p times x plus the inlet temperature. Here, this temperature variation of the fluid is not going to be linear. We can see here that it's, it's going to be nonlinear with a decaying exponential in the definition of that temperature. Now, how do we get to that? Well, we can do that by considering an energy balance on a section taken out of this pipe. If I consider here a small section taken out, I can consider that there's energy that comes in with the fluid, m dot C sub P times T sub M. That's an expression of the enthalpy of the fluid coming into the control volume. An expression of the temperature, or the enthalpy coming out in terms of the temperature here. So this is m dot C sub P times Tm plus dTm. dTm is an infinitesimal change in the temperature as we go through an infinitesimal distance through the pipe here. And if we have a heat flux, or let's say here, this would be a heat transfer rate into the fluid, well, that heat transfer rate would just be the heat transfer coefficient times Ts minus Tm times a small area. What would the area be? Well, the area would be this dx, a distance, times the perimeter around around the pipe. So this is just an expression that we can use for the energy balance of the fluid, or energy balance on the fluid. So the energy comes in with the fluid, energy comes in with the heat transfer, energy leaves with the fluid. So if I write this expression out just as an energy balance, the expression says that m dot C sub P Tm plus H times Ts minus Tm. And here, instead of writing dA, I'm going to write the expression of this area over which the heat transfer would be occurring, which would just be that inner surface area, would just be the perimeter times dx. Here again, where P is just the perimeter of the pipe. And I'm leaving it as just perimeter because it could be a circular pipe or it could be a square pipe. But we can always determine what that perimeter is just by measuring the length of the sides. So this is energy in with the enthalpy, energy in with the heat transfer by convection, and the energy out, which would be m dot C sub P times Tm plus dTm, where again, dTm is just a small change in the temperature due to the heat transfer that comes in through this very small surface area. If we reduce this expression, m dot C sub P times Tm and m dot C sub P times Tm can be subtracted from both sides of the equation, and we're left with an expression that says H times Ts minus Tm times the perimeter times dx is m dot C sub P times dTm. So here we have just the heat transfer that's occurring through this surface is equal to the change in the enthalpy that would exist, where that enthalpy is represented as C sub P times T. And so if we consider this expression, then this becomes a starting point for determining the expression of the change in the temperature of the fluid as a function of X. Now here I'm going to let dTm be equal to a minus d times Ts minus Tm. Now here, this is okay because Ts is a constant. So if dTm is a temperature differential for the fluid, I'm just going to define it as minus dTs minus Tm, because if I take the derivative of this expression, there's the change in the surface temperature with respect to position, since it's flat, is a 0. So this expression of minus d of Ts minus Tm is the same as dTm, because this expression that becomes exactly that, because Ts, or the change in Ts, is equal to 0. And so with the minus sign multiplied by dTm, I get exactly the same expression. If I make this substitution into the equation, this expression becomes H times Ts minus Tm times P times dx is equal to minus m dot C sub P d of Ts minus Tm. Now notice also that Ts minus Tm is this expression of the temperature difference that changes along the length, where that temperature difference is the difference between the surface temperature and the fluid temperature. So with this expression, now I can group some terms, And if I group terms, here the heat transfer coefficient here is going to be what we consider and if we evaluate it based on an average heat transfer coefficient along the length of the pipe, it's not a function of X. TS is not a function of X. The mass flow rate and specific heat are also not a function of X. So if I group terms so that I have all the temperatures on one side and all of the expressions of constants on the other side, then I can write this expression as H times P divided by M dot C sub P, and I'll move the minus sign over to the left side, times dx is equal to 1 over Ts minus Tm dTs minus Tm, like this. So written this way, I have all of these constants, the perimeter of the pipe, the heat transfer coefficient as an average value, the mass flow rate and specific heat, all of those are constants. And here I have 1 over Ts minus Tm times dTm. So if I integrate this expression, integrate from x equals 0 to x equals L, which is just the length of the pipe, then this expression becomes the integral from 0, let's say I'll say, yeah, from 0 to L of minus HP over M dot C sub P dx is equal to the integral here at x equals 0, the temperature is the inlet temperature, and at x equals L, the temperature is the exit temperature. So I'll write this as 1 over Ts minus Tm dTm, dTs minus Tm, like this. So here the expression, if we evaluate this, HP M dot C sub P, all of those are constants. So the left-hand side of this equation becomes minus HP over M dot C sub P times L minus 0. And the right-hand side of the equation becomes the natural log of the surface temperature minus the exit temperature divided by the surface temperature minus the inlet temperature. So if I want to solve for the exit temperature, I rewrite this expression as the exponential of minus HP over M dot C sub P times L is equal to Ts minus Te divided by Ts minus Ti. Well, again, where the Ts is the surface temperature, Te is the exit temperature of the fluid from the pipe, and Ti is the inlet temperature of the fluid into the pipe. And here, if I solve for the exit temperature, this expression just says that the exit temperature will be the surface temperature minus the surface temperature minus Ti times the exponential of minus HP over M dot C sub P times L. So this allows me to consider or calculate what the temperature at the exit is. And here the temperature at the exit of the pipe is based on us going all the way to x equals L. If I want an expression for just the temperature of the fluid as a function of the length of the pipe, then this becomes Tm as a function of x, will be still the surface temperature minus the surface temperature minus the inlet temperature times the exponential of minus HP over M dot C sub P just times x. And so we can see here when x is equal to 0, this term becomes a 1, and I get Ts minus a Ti. So the surface temperatures will cancel, and I'm left with a positive value for Ti, which just says when x is equal to 0, yes, the temperature at the inlet will be exactly equal to 0. Exactly equal to the temperature that is Ti at x equals 0. So, and as x goes to infinity, this term goes to a 0, And all I'm left with is the temperature of the fluid at x equals infinity would just be the surface temperature, which would be the limiting temperature here. The highest temperature that this fluid can come out of the pipe at would be the surface temperature that is a constant here. So this expression then becomes an expression for the fluid temperature as a function of x when we have a constant surface temperature that exists on the wall. Now, how do we determine what the heat transfer rate is into the fluid? Well, here, again, these red arrows that I've drawn represent the delta T for the heat flux from the surface into the fluid. So here, whatever the average heat transfer coefficient is, or here actually we can consider local values of the heat transfer coefficient times the temperature difference between the surface and the fluid will give us that local value of the heat flux. But a heat transfer rate is equal to a heat flux over the surface times that surface area. Well, the surface area will be the entire inside surface of the pipe, but we know that the temperature difference between the surface and the fluid changes as we move along the length of the pipe, and the heat transfer coefficient actually locally changes along the length of the pipe until we get to the fully developed condition. So in order to write an expression for this heat transfer rate, we consider the average heat transfer coefficient, the same value of the average heat transfer coefficient in the expression of the temperature variation of the fluid as a function of position. And we can write an expression of the heat transfer rate that is this average heat transfer coefficient times the entire surface area on the inside of the pipe, but this will be multiplied by an expression of delta TLN, as it's referred to in your text. And that is what's called the log mean temperature difference. And the log mean temperature difference is what we use to express an average temperature difference that occurs along the length of the pipe when one or both of the temperatures changes logarithmically. And here, the mean temperature of the fluid changes with a natural log expression, or an exponential expression here, that is written in terms of a natural log when defining the ratio of the temperature difference between the exit and the inlet here. This log mean temperature difference can be defined delta TLN is the temperature difference that exists between the surface and the fluid at the exit minus the temperature difference that exists between the surface and the fluid at the inlet, divided by the natural log of the temperature difference between the surface and the fluid at the exit, divided by the natural log, divided by the delta T at the inlet. Where here, this expression of delta TE is the surface temperature minus the temperature of the fluid at the exit, and delta TI is the surface temperature minus the temperature of the fluid at the inlet. And again, the reason we use this expression has to be used is because this temperature variation is one that is varies with a natural log expression or a decaying exponential. And so this temperature difference is not linear. And so all this expression gives us is the average value based on the inlet temperature difference and the exit temperature difference with a natural log variation between the two. So this expression, the only time you'll use this log mean temperature difference when considering internal flow through a pipe is when you do have a constant surface temperature problem. This is not an expression that is needed for the expression of a temperature variation along the length of a pipe that has a constant heat flux, because in a constant heat flux, the heat flux is constant over the entire surface of the area, or surface area of the pipe. In a problem where we have a constant surface temperature, the heat flux is not constant along the length. So we have to use this expression in order to write an expression for the heat transfer rate. So when we're considering one of these problems, whether it's a constant surface heat flux or a constant surface temperature problem, these are the expressions that we would need in order to solve the problem. If I have a constant heat flux problem, the heat transfer rate is just that constant heat flux times the entire surface area on the inside of the pipe. Here, the surface temperature of the fluid can be written as a function of X, and also the mean temperature of the fluid can be written as a function of X. So those three expressions, temperature variation of the surface of the pipe, temperature variation of the fluid in the pipe, and the heat transfer rate are all calculated by these expressions. When we consider the expression of the of a problem where we have a constant surface temperature, the heat transfer rate will be the average heat transfer coefficient times the surface area times the log mean temperature difference. The temperature of the fluid as a function of X, and we don't need an expression for the surface temperature variation because the surface temperature does not vary. It's a constant in this problem. So those expressions are ones that we would use, and we always can write, no matter whether it's a constant heat flux or a constant surface temperature problem, the heat transfer rate into the fluid can always be written as Q dot is equal to the mass flow rate times the specific heat times the temperature at the exit minus the temperature at the inlet for the fluid. So that becomes an expression that allows us to define a heat transfer rate, whether we know how heat is being delivered or not. This expression of a change in entropy of the fluid is representation of all the heat that goes into that pipe. So when we're writing these problems or writing up a problem statement, we have to consider the expression of how is heat getting into the pipe. Is it by constant surface temperature or is it by constant heat flux? But then we have an expression that allows us to consider how the temperatures vary if it's a constant heat flux problem, and also for a constant surface temperature problem, and how we would actually calculate the heat transfer rates. But in order to write those expressions, or in order to make the calculations, for the calculation of a heat transfer rate, we need a heat transfer coefficient. For a calculation of the temperature of the fluid as a function of X, we need the heat transfer coefficient. That's for the constant surface temperature problem. For the surface temperature problem, we need the heat transfer coefficient. If we want to find the surface temperature. For the mean temperature of the fluid, we don't need the heat transfer coefficient. All we need to know is what that heat flux is. So when we're writing an expression for the determination of temperatures or what's happening actually in the problem as far as heat transfer goes, we need a way to find out, well, what is the heat transfer coefficient? Well, the heat transfer coefficients are going to be dependent on the flow condition. So if we want to calculate let's say for H determination, we have to answer two questions. Is it laminar or turbulent? And is it developing or fully developed? So the laminar or turbulent is a question of, is the Reynolds number greater than 2300? If it's less than 2300, it's laminar. If it's less than 2300, it's going to be laminar. If it's greater than 2300, we're not going to treat it as laminar, even though it's not considered to be fully developed. If it's less than 10,000. So we'll use the same conditions as I specified before. If it's laminar, if it's less than 2,300, considered to be fully turbulent if above 10,000. But if it's above 2,300, we definitely will not use laminar correlations. Typically, we will still use the correlations for fully turbulent problems. Developing or fully developed, that has to do with how we're going to treat that entrance region. So we'll be considering, well, what is the entrance region length compared to the pipe length? So if it's a laminar flow, we had these expressions. I think they're on the other page here. The pipe length, or the entrance region length that we're going to compare to the pipe length, well, that entrance region length is going to be calculated as 0.0. Let me just try to put it on the page here. Here we go. For laminar flows, particularly the thermal intra-region length is where we're going to be considering, well, where is the heat transfer coefficient variation occurring? And that thermal intra-region length, if the Reynolds number is less than 2,300, we'll calculate how long the pipe, or how long that entrance region is, so that we can compare it to the pipe length, and then consider, can it be averaged out, or do we have to actually take into account what the value is there? And if it's a turbulent flow, where the Reynolds number is greater than 10,000, fully turbulent, above Reynolds number of 10,000, the hydrodynamic and the thermal intra-region lengths are both approximated to just be 10 times the diameter of the pipe. And so we would compare that length to the overall length of the pipe. Typically, if the pipe length is 10 times the value of the entrance region, we can completely ignore what's happening inside the entrance region. So here I'm just going to write up and consider a problem that allows us to calculate these quantities. So a pipe with a constant heat flux. So that will look something like this. If I have this pipe where a constant heat flux is applied to the surface, and here we would have to specify, of course, the diameter and the length of the pipe. And we'll consider here that we want it to experience a given temperature variation. The temperature at the inlet to the temperature at the exit. And for a given mass flow rate, here, just draw it this way, we'd consider, well, what would the average heat transfer coefficient need to be in order to solve this problem? So here, the mass flow rate, we'll take it 0.01 kilograms per second. The inlet temperature and the exit temperature here, 50 degrees and 150 degrees. The length of the pipe at 15 meters and the diameter at 25 millimeters. So very small. And we'll hear the diameter, anytime you see a diameter in the internal flow problems, that is the inside diameter, inner diameter of the pipe. So that's where the fluid is flowing through. And we could consider that this heat flux might just be by an electrically resistive tape that's on the outside to provide this heat flux. And we want to consider, well, what is the average heat transfer coefficient that would exist for, we'll consider water and air, two very different fluids that would flow along the length of this pipe. So here, I'm going to pause here so you have like the 5 minutes or so to prepare your workspace for your exam. but it will open up in 5 minutes, and I will be in. I'll stay in this. I'll keep this session open so that if you have a question, you can come back into this Blackboard Collaborate session and and ask a question for